Okay, so let's take some time and talk a little bit about the course itself and the various components of the course. But first, I want to give you a little bit of background in the theory behind designing a course. This is probably the most designed course that I teach. Everything that we do this semester is going to be for a reason, and so I want to kind of fill you in on a little bit of the reasoning behind the decisions that I've made as I designed this course. So I designed this course based on something called backwards design. So the idea is you kind of start with some big ideas that I want you to sort of internalize and really understand. And some of these are somewhat vague. So here's a particular big idea. So a compiler is a large software system consisting of a sequence of phases. So this is sort of a grand idea. And what I've done then is I've taken those big ideas and I have attempted to delineate what exactly I would like for you to be able to remember 5 years from now. For instance, if you come back as an alumni, these are the sorts of things that I would want you to still be able to know and do. So for instance, large problems can sometimes be solved by composing existing solutions to smaller problems. And hopefully you can see how this is sort of it's kind of elaborating on this big idea, right? It's something a little bit more specific, but it's also something that is going to continue to be useful to you in your career even after you finish with this course. So from the enduring understandings, then I can then begin to enumerate the actual learning objectives. So how do we get to those enduring understandings in the context of this course? So this is the stuff you should be able to remember at the end of the course. Maybe not 10 years from now, but these are the things that at the end of the semester you should be able to readily recall and do. So for instance, identify the technical challenges of building a large software system such as a compiler. Once we have sort of this theoretical framework, then I take these things and I build the actual assignments and the activities that we do in the course. So for instance, draw a diagram illustrating the major phases of a modern compiler. So this is kind of the big idea, the enduring understanding, and the learning objectives, now worked out in sort of the nitty-gritty ways that we're actually going to go about learning these things over the course of the semester. The exams are going to directly reflect the activities, the labs, and the quizzes, and the things that we do in class. And so the goal here is engaged and effective learning. I know that engaged is a term that gets thrown around a lot and sometimes lacks some concrete meaning, but I like the term effective here because my goal as an instructor is to make sure that the time that you spend in class and working on the things that I've assigned to you are far more effective for learning this material and reaching those enduring understandings than anything that you could be doing on your own. And so that's really my goal in this course. So here are the learning objectives for this course. I'm not going to sit here and read all these to you. They're in the syllabus, and so you can go and look at them if you're interested. But these are the things that, by the end of the semester, you should be able to look back over these and tick these off and say, yep, I know and can do all of these things. So the course website has everything that I can post publicly. I am a big believer in freely available information, and so I try to post everything that I have the ability to post. Obviously, solutions and things like grades can't be posted online, so we'll be using Canvas and some other systems for those things. But as much as I can is posted online. There is a different version of the website for each year, and so make sure that you're using this year's website. So at the top of the screen, it should always say this year. The general weekly schedule goes as follows. So this is designed to be a Monday, Wednesday, Friday class. So on Monday, we have a recap and a new topic introduction. This is sort of takes the form of a lecture, but it's intended to be interactive. So there'll be lots of opportunities for discussions. After that introduction, then the idea is that you would then take the rest of Monday and Tuesday to go and read the assigned reading for the week and do that initial reading quiz. And you generally get 2 attempts at those quizzes so that you can go back and do some rereading if you need to. On Wednesday, then, we'll come in, we'll answer any questions that you have, and with any time that is left over, generally we'll be working problems. Thursday, then, if you need to do more reading, you can do some more practice. But basically, the goal is to get ready so that on Friday you can come in and begin working on the labs, which are essentially problems that are the kind of problem that I would give you on an exam. And so basically the entire week is built around achieving some sort of level of mastery over the concept for that week. There will also be projects obviously going on throughout the semester, and so you need to be mindful of that and making sure that you allocate enough time to work on those projects every day of the week, not just the days that we meet in class. There is a distinction that I like to make between formative and summative assessments. So a formative assessment is one that's sort of primarily aimed at helping you learn. A summative assessment is one that I use to assess whether you have learned or not and evaluate you. And so in that way, it's less important to me that you get all the answers right on a formative assessment. It's more important that you use the process to learn. And then, of course, hopefully by the time you take a summative assessment, you will have learned the things that you need to learn. And so to that end, I tend to put less weight on the formative assessments. And so I believe in this course, it's roughly a fifth of your full grade devoted to formative assessments and roughly 4/5 devoted to the summative assessments. So formative things are generally the quizzes and the labs, and the summative things are the projects and the exams. These are the course textbooks. So our primary textbook is Engineering a Compiler. This is a pretty nice textbook. It's very hands-on and practical. I have scanned the first chapter and it's posted on Canvas for those of you who haven't yet been able to acquire it. The second textbook that we'll be drawing from a little bit is the Classic Compilers textbook, sometimes referred to as the Dragon Book because of the picture on the front. This is considered to be the definitive text on compilers. It's a bit theory heavy for an undergraduate course. We're going to be using it for, we're going to be using 2 chapters of it, and I have those scanned and accessible on Canvas. We're not going to be using the rest of that book. There are also references to both decaf and ILOC, two new languages that we're going to be using this semester, and those PDFs are posted on the website. So, of course, the semester-long project is a major component of this course. You will be implementing the major components of a compiler for this language called decaf. This compiler is going to be implemented in C, particularly the C11 standard for C. We have a make build system with a fully integrated test suite, and we are going to compile this decaf language down to something called ILOC, which is machine language that our textbook uses. There's also a conversion that I'm going to provide to convert the ILOC into y86, which is going to very nicely close the loop that you started with CS432, where you learned about y86 and you wrote an interpreter for it. So at the end of the semester, you'll be able to take programs written in decaf, run them through your compiler that you wrote in this course to generate the equivalent y86, and then you'll be able to run the y86 using the y86 interpreter that you wrote in 261. So I think that forms a very nice kind of sort of a nice final concluding note for the system sequence here at JMU. Okay, so there are going to be 5 major projects, pieces of the full system. We'll talk more about that in a bit. There is going to be sort of a multi-phase submission for all of this. So you're going to submit your code. You are going to also do a code review. So you're going to be assigned someone else's submission, and you're going to write a review, and then you're going to respond to that review just with a very brief, this was useful or this was not useful. So the code itself, so doing the project can be done in teams of up to 2. Working with someone else on the project comes with both benefits and costs. So I would encourage you to be careful about choosing to work together in a team. But I will say that it is generally advantageous to work in a team. It generally helps to have someone else to bounce ideas off of and to share the work. Although you do also have to then deal with integrating the different parts together. But in any case, you'll be working on that possibly in teams, but the code reviews will be individual. So everybody will be doing their own code review, and those are going to be due a week after the original submission. And then, like I said, that review response is going to be a pretty basic, just how did your reviewer do? All right, so that summarizes the major components of this course.